Hello there. As you all have probably already been introduced to, the arithmetic mean x bar is defined to be equal to 1 divided by n multiplied by the sum from k is equal to 1 to n of our values xk. Here, xk belongs to some sample. And this is what we refer to as the arithmetic mean. And some people even refer to it as the average. In this video, we'll introduce what we call the geometric mean. So the geometric mean, which is defined to be equal to, so let's just call it gm of s. And this is defined to be equal to the nth root of the product from k is equal to 1 to m of xk. Here, xk belongs to our sample. So before we get into the calculation, I just want to make sure that this notation that we're using here is familiar to the audience. So what this capital Pi means is the product, sort of like capital Sigma means sum. So we can rewrite this in another way. We can rewrite this as the nth root of x1 multiplied by x2 multiplied by x3 times up to xn. And this nth root can be written using fractional exponents, so one can write this as the product of x1 times x2 all the way out to xm, all raised to the power 1 divided by m. So this is the geometric mean of a particular sample. So let's do an example on how to calculate the geometric mean for a set. So example. Let's assume we have a sample of, say, the numbers 3, 5, 8, and 10. So if this is true, then that means the geometric mean of S is equal to the fourth root of 3 times 5 times 8 times 10. So this is equal to, so once you do 3 times 5 times 8, so that's going to be 8 times 5 is 40, 40 times 3 is 120, times 10 is going to be 1200. So this is just going to be 1200 raised to the power of 1/4. With the calculator or some other methods, you can find this is approximately equal to 5.886. One important note here, since we're taking radicals, so if this index is even and this radicand is negative, then you cannot use it. So the geometric mean of a sample is not defined if n is even and the number of elements that are negative are odd. Because if you multiply an odd number of negative numbers, you're going to get a negative number back, and you can't take even roots of negative numbers. But in general, one can just say GMS of samples with negative entries. We can say is not defined. But this is more of a stronger or less that of a restriction in terms of this last one. Unless you want to introduce complex numbers into the picture, particularly for a basic stats class, this is not something of interest. So let's talk about a couple properties that one may have here. So property 1. So let's assume we have a set and we have, say, x1, x2, x3, out to, say, xn. And actually, let's call this set sample x. Let's also consider another sample y, say containing y1, y2, y3, all the way out to yn. So what would the geometric mean of x be? So the geometric mean of x is going to be equal to the nth root of x1, x2, all the way down to xn, and the geometric mean of y is going to be equal to the nth root of y1 times y2 all the way out to yn. So based on these two, we can actually get a useful identity for the geometric mean. So what is the geometric mean for the set xy? So I'm going to define x over y to be equal to the quotient of corresponding entries. So x1 over y1, x2 over y2, x3 over y3, all the way down to xn over yn. And if x and y are different sizes, you can be clever by multiplying by 1 and have a slight variation of this identity. So this is going to be equal to the nth root of x1 over y1 times x2 over y2 all the way down to xn over yn. So by properties of fractions, we can rewrite this as the nth root of x1 times x2 all the way down to xn all over y1 times y2 all the way down to yn. By properties of indices for radicals and also exponents, we can rewrite this expression as the nth root of x1 times x2 all the way down to xn all over the nth root of y1 times y2 all the way down to yn. So the numerator is precisely the definition of the geometric mean of x, and the bottom is precisely the geometric mean of y. So therefore, we have that the geometric mean of the quotient of entries is equal to the quotient of the geometric means. And one can find that this is a very unique property for the geometric mean. Another common property that is used in both theory and applications is the following, which is sometimes referred to as the AMGM inequality. So the arithmetic mean, geometric mean inequality says that the arithmetic mean of a set is always greater than or equal to the geometric mean of a set. In formula ways of writing, that means if you have 1 over n times the sum from k is equal to 1 to n of xk, this is always going to be greater than or equal to the nth root of the product from k is equal to 1 to n of xk. So for n is equal to 2, we have that the square root of xy is always less than or equal to x plus y over 2. If you want to practice your theory skills, you can try to prove this type of thing. So proof left as an exercise, in case you're interested. And if you want to try and prove the more general result for the AMGM inequality, you definitely need to have some more stronger pre-calculus skills to use that. So now let us work out a particular example for which you may want to use the geometric mean. So example. So suppose you measure a bacteria population and it grows by, say, 40% in the first hour, 52% in the second hour, and let's say it grows by 47% in the third hour. So on average, what is the percent increase growth for the bacteria per hour? So a couple numbers here, 40%, 52%, and 47%. So let's look at this in a more basic idea. So we're going to let P0 represent the initial population. So if P0 is the initial population, then after the first hour, P1, this is going to be equal to P0 multiplied by the percent growth. So this is going to be 1 plus 0.40, or equivalently P0 times 1.4. If the next growth is 52%, then P2 is going to be equal to P1 multiplied by 1.52. That's going to give you 50% more than P1. And if it grows 47% from P2, then P3 is going to be equal to P2 multiplied by, 47%? So 1.47. All right, so we can pretty much nest these things here, because what is P2? Well, P2 is just going to be equal to P1 times 1.52, all multiplied by 1.47. And then we can replace P1 with its definition here. So we have P3 is actually equal to P0 multiplied by 1.4 times 1.52 times 1.47. So this is going to be the result of your result. So let's suppose that P0 is, 100 number of bacteria, I guess you could call it. So this means that P3 is going to be equal to, so the population after 3 hours. So this is going to be equal to 100 times 1.4 times 1.52 times 1.47. And you can find that this is equal to 312.816. And I guess that you could round that to, say, 313 if you want. So actually, if you want to find the average increase per hour, what you're actually looking for is the geometric mean. And I'll explain why in just a moment. So the geometric mean of these growth factors, so this is going to be equal to the cube root of 1.4 times 1.52 times 1.47, which one can find to be approximately equal to 1.463. So what you can do actually is you can take the original population and you can multiply it by this number, 1.463 times 1.463 times 1.463, or in more compact notation, 1.463 cubed, and you can find out that if P0 is equal to 100, then P3 is equal to 100 times 1.463 cubed is actually approximately equal to 312.816, which is actually the number that we had before. So I hope you enjoyed this video to give you a sort of insight on the geometric mean. So in general, if you want to know the average increase of a population, if it is multiplicative, you'll tend to use the geometric mean. But if the average is, say, increasing in an additive fashion, then you're going to most likely be using the arithmetic mean, or the average, to sort of calculate that average increase. Hope you enjoyed.